Okay, so today we're diving into quantum teleportation, but not the Star Trek kind. We're talking about teleporting information over the internet we use every day.
Exactly. And the fascinating part is we're not beaming up Scotty or anything. We're talking about the quantum state of a particle. So it's like its properties, not physical matter being moved.
So it's more like sending a secret message, one that disappears from where you wrote it, but then it just pops up somewhere else miles away.
Yeah, that's a good way to put it. And what's really remarkable about the research we're looking at today is they managed to do this over 30 kilometers of regular fiber optic cable. The same stuff that carries all our internet traffic.
Wow, so cat videos and quantum information sharing the same lines. But hold on, the sources we read mentioned this quantum state is incredibly fragile, like super easy to disrupt.
Huh?
So how do you send something like that through all the noise of the internet without it getting completely scrambled?
Well, that's the breakthrough here. They figured out how to use specific wavelengths of light to kind of minimize the interference from all that other internet traffic. It's like finding a quiet channel on a radio that's just bursting with chatter.
Okay, I kind of get that. But why is this such a big deal?
Yeah.
Why is sending quantum information over our existing internet so groundbreaking?
Well, think about it. Imagine communication that's basically unhackable. Since the information doesn't actually travel in the conventional sense, it's incredibly difficult to intercept.
So you're saying things like online banking, medical records, all that could be truly private.
Exactly. But it goes even further than just security. Imagine networks of quantum computers all linked together by teleportation. We're talking about processing power that's just mind-blowing.
Okay, you've definitely got my attention. So what kind of real-world applications of this are you most excited about?
For me, it's the potential for sensing applications. Like, imagine quantum sensors that can pick up on tiny changes in the environment, or even in the human body. We could diagnose diseases incredibly early on, or monitor environmental shifts with incredible precision.
So earlier disease detection, more targeted treatments.
Yeah, exactly.
This is amazing stuff. All right, so we've got the what and the why, but let's dig into the how. How does this quantum teleportation magic actually work?
Well, it all comes down to this mind-bending concept called entanglement.
Entanglement. All right, this is where I might need you to break it down for me.
So entanglement is when two particles become linked in a way that they share the same fate, even if they're separated by huge distances. Change one and the other changes instantly.
Whoa. Okay, that's a lot to wrap my head around.
Think of it like two coins flipped at the same time. They always land on opposite sides, even if they're miles apart.
Okay, I sort of get that. But how does that spooky action at a distance, as you called it, actually enable teleportation?
Well, with entanglement, you can actually transmit information instantly without having to physically move the particle that's carrying it.
So instead of sending the actual message, you're using entanglement to kind of beam the information from one place to another.
Exactly.
That's incredible. But I'm guessing there's got to be some catches, right? What are the challenges we need to overcome before we're all teleporting information?
Yeah, so we're still in the early stages here. There are limitations on how far we can reliably send information this way. And there are limitations on how accurate the information is when it arrives, what we call fidelity.
So the message might not always arrive perfectly.
Yeah, kind of like a fuzzy radio signal sometimes. But researchers are working on overcoming these limitations, increasing the distance, and improving the fidelity so the information arrives intact and error-free.
And how about making this work with our existing internet infrastructure?
That's another big challenge. But the research shows that quantum and classical data can actually coexist on the same network. So we might not need to build a whole separate quantum internet.
So you're saying a future where we have this incredibly secure, powerful quantum layer built right into the internet we use every day.
That's the vision.
Yeah.
And this research is a major step towards making that a reality.
Well, this is some truly mind-blowing stuff. This quantum future is both incredibly exciting and a little bit intimidating. But before we get ahead of ourselves, we'll be back after a quick break to dig a little deeper into the specific challenges and opportunities that lie ahead in this quantum world. So stick with us.
See you in a bit. Welcome back.
All right, so before the break, we were talking about all this amazing potential, ultra-secure communication, quantum computing networks. But let's break it down a bit. Let's start with cybersecurity. How exactly would quantum teleportation make our data unhackable?
Well, with traditional encryption, it's all based on complex math. But with enough computing power, you can crack it. Quantum teleportation is different. The information doesn't actually travel through the network. It disappears in one spot and then reappears somewhere else because of that entanglement link we talked about.
So there's literally nothing to intercept. It's like sending a message with disappearing ink.
Yeah, that's a good analogy.
Like I said, that's cybersecurity. But what about these quantum computing networks? You were saying that linking these computers together could create unimaginable processing power.
Right, so quantum computers are fundamentally different from the computers we use today. They use quantum mechanics to do calculations in ways that classical computers just can't.
So if you connect multiple quantum computers together, you create a network that can solve problems that are impossible even for today's most powerful supercomputers.
Exactly.
So what kind of problems are we talking about?
I mean, think about designing new materials with specific properties, or developing personalized medicine based on an individual's DNA, even unlocking some of the deeper mysteries of the universe.
Wow. Okay, so problems that would take regular computers centuries or maybe even longer to solve.
Right.
And then there's the potential for quantum teleportation and sensing.
Right.
You mentioned these incredibly precise sensors that could detect the tiniest changes.
Yeah, like imagine a sensor that could pick up on minute variations in gravity. We could map the Earth's subsurface with incredible accuracy, which could lead to new discoveries in geology and resource management.
Or what about a sensor that could detect subtle changes in magnetic fields?
Right, then we could diagnose brain disorders with much higher precision.
So we're talking advancements in fields like geology, medicine, even space exploration.
Exact.
All thanks to these quantum sensors. It's amazing to think about. But realistically, how long will it be before we actually see these technologies in action? Will I see a quantum computer in my lifetime?
That's the big question. And it's hard to say for sure. We're still in the early stages of research and development.
So what are some of the biggest challenges standing in our way?
Well, one of the biggest is scalability. Right now, quantum computers are still relatively small and limited.
So we need to figure out how to build bigger and more powerful quantum computers.
Exactly. And that requires breakthroughs in a lot of different areas like materials, science engineering, computer science.
It's a huge undertaking. What about challenges specific to quantum teleportation itself?
Right. Well, distance and fidelity are still major hurdles. We need to be able to teleport information over much longer distances without losing anything. And we need to make sure the information arrives perfectly with no errors.
So we need to make that disappearing ink signal stronger and more reliable.
Precisely.
So that we can teleport information accurately across vast distances.
Exactly.
And of course, there's the challenge of making all of this work with the internet we already have.
Well, we can't just rip out all the cables and start over.
We need to find a way to integrate these quantum technologies with our existing systems.
Exactly.
It's a complex puzzle.
But researchers are making progress.
It sounds like there's still a lot of work to do.
Yeah.
But it's encouraging to hear about all the advancements being made. What are some of the most exciting developments you're seeing right now?
Well, one area that's really exciting is the development of quantum repeaters. These devices could help us extend the distance over which we can send information, potentially leading to a global quantum communication network. Yeah, it's like having signal boosters, but for quantum information.
So they help that disappearing ink travel further without fading out.
Exactly. And another area that's really promising is quantum memory. It's like a hard drive, but for quantum computers, allowing us to store quantum information for longer periods of time.
Okay, so storing and boosting that fragile quantum information. Sounds like we're making some real progress towards making all of this practical. What do you think the next few years hold for this technology? Any predictions?
Well, I think we're going to continue to see really rapid progress, especially in quantum computing and communication. I wouldn't be surprised if we start seeing some real-world applications of quantum teleportation within the next decade.
Wow, so we might be living in a quantum world sooner than we think. That's both exciting and a little bit daunting. But we've been focusing on all the positive stuff here. Are there any potential downsides or risks that we should be thinking about?
Oh, absolutely. Like with any powerful technology, there's always the potential for misuse. For example, quantum computers could be used to break the encryption we use today, which would be a huge threat to cybersecurity.
So the same technology that could make our data unhackable could also be used to hack into systems that rely on traditional encryption.
Exactly. It's a double-edged sword. And it really highlights the need for responsible development and regulation of these technologies.
To make sure they're used ethically and for the benefit of everyone.
Right.
Are there any other potential risks that you're thinking about?
Well, one concern is job displacement. As quantum computers become more powerful, they could start automating tasks that are currently being done by humans, which could have a big impact on the workforce.
So we need to be thinking about the economic and societal implications of these advancements as well.
Absolutely. It's not just about the technology itself. It's about how we as a society choose to use it.
That's a really important point. Well, we've covered a lot of ground today, from the mind-bending science behind quantum teleportation to all of its potential to change the world as we know it. But before we wrap up, I want to leave our listeners with something to think about. Imagine a world where all of this is commonplace. Instant, secure communication across huge distances, unimaginable computing power, sensors that can detect the tiniest changes in our world. What would that world look like? How would it change our lives? It's a pretty amazing thing to think about. As we stand here on the edge of this quantum revolution, thank you for joining us on this deep dive. If you're interested in learning more, be sure to check out the links to all the research and articles we talk about in the show notes. Until next time, keep exploring, keep questioning, and keep wondering.